Alright, now we look at this problem about the optimization. So we are given a function f, which is given by the natural log of x squared plus x plus 3. And for the first part, we want to find the absolute maximum and the absolute minimum on this closed interval from -1 to 1. So by the extreme value theorem, we know that on this closed interval, this function must have the absolute maximum and the absolute minimum. So here we need to take care about the two parts. So the first part is the local max and min, and the other part is the function value of the endpoints. Okay, so we firstly take care of the local max and local min. So by saying local maximum and local min, to find them, we need to take the derivative of f, and firstly, because it is log, we're going to take the derivative of log first. So that is 1 over x squared plus x plus 3, and then times the derivative of the inner function, that is the derivative of x squared plus x plus 3. So we know that it is, and for this part, its derivative is given by 2x plus 1. So if we combine the two pieces together, we know that f prime is given by 2x plus 1 over x squared plus x plus 3. Okay? And then we're going to find the critical point, that is when f prime equal to 0. And then, because it is a fraction function, so the only possibility that f prime can be 0 is when, so that is we want 2x plus 1 over x squared plus x plus 3 equal to 0. The only possibility will be the numerator 2x plus 1 equal to 0, because the denominator can never be 0. So here we know x is equal to -1/2. Okay? But we have no idea about whether this x equal to -1/2 is the local maximum or the local minimum. So we're going to use the second order derivative test. Okay? So that means we're going to find f double prime. And because this is a fraction function, we're going to use the quotient rule. That is given by the denominator is x squared plus x plus 3 squared. And then for the numerator, it is the derivative of the original numerator times the denominator minus the original numerator, 2x plus 1, times the derivative of the original denominator. Okay? So we can see that this part is just 2, and this part is equal to 2x plus 1. So if we combine them together, we still have this denominator square, and that is 2 times x squared plus x plus 3 minus 2x plus 1 square. Okay? And if you expand this out, you will have, for the numerator, it is -2x squared minus 2x plus 5 over x squared plus x plus 3 square. Okay? So we can see that the denominator is always positive, and it is sufficient to check the numerator. So we're going to plug -1/2 in, and we have -2 times -1/2 squared minus 2 times -1/2 plus 5. If you calculate this out, it is equal to 8 over 11, which is greater than 0. So when x equals to -1/2, fx achieves to a local minimum. So local mean is equal to f -1/2, and if you calculate this out, it is equal to natural log of 11 over 4. Okay, this is the local max and local min. There's no local maximum for this problem. We only have a local minimum. Alright, this is the first part for the local max and local mean, and then next we're going to take care about the endpoints. So we have the endpoint, we have two endpoints, that is -1 and a +1. So we firstly plug in -1, and by the algebra it is equal to natural log 3. And for the other endpoint, that is when x equal to 1, we have natural log of 5. Okay, and then we're going to compare the function value of those three values, because we know that 11 over 4 is less than 3 is less than 5, and then that means natural log of 11 over 4 is less than natural log 3 is less than natural log of 5. So the function f achieves the absolute minimum at x equal to -1/2, and the corresponding function value is natural log of 11 over 4. So absolute minimum is f -1/2 equal to natural log of 11 over 4. And when x equal to 1, this function f achieves its absolute maximum. So the absolute maximum is equal to f1 equal to natural log of 5. Okay, so this is absolute minimum, and this is absolute maximum. Alright, this is the first part, and then we're going to look at the second part. We want to determine, it is still the same function as before, we want to determine on this interval from -1 to 1, it is function concave up, concave down, or neither. Okay, so remember, if we want to talk about concave up or down or neither, we're looking at the second order derivative. Okay, so I'm going to steal the result from the first part to here, and we know that f double prime is equal to -2x squared minus 2x plus 5 over x squared plus x plus 3 squared. Okay, and we know that if f double prime is greater than 0, and then that means it is concave up. If f double prime is less than 0, it is concave down. So that means we're going to tell the sign of the f double prime to do this problem. Alright, then if we look at this f double prime function carefully, we can see that for the denominator it is something square, it is always positive. So it is sufficient to look at the numerator, and we need to tell the sign of -2x squared minus 2x plus 5 on the interval from -1 to +1. Okay, and here we are going to do a complete perfect square problem to determine the sign of it. So remember what you learned in pre-calculus, I guess. We are going to complete the perfect square, we firstly factor out the coefficient of the x squared, that is -2 here, and together factor out the same coefficient of the x. Okay, and then we have -2 times x squared plus 2 times 1/2 times x plus some other constant b squared, and then minus b squared, so nothing changed here, plus 5. Why do I add and subtract b squared? Because I want to use the perfect square formula, that is a plus b squared equal to a squared plus 2ab plus b squared. Okay, so our a here is equal to x, and our b here, by looking at this part, it is 2 times a is x, and b is the other number, so b here is equal to 1/2. Okay, so after figuring out b, we have -2 times x squared plus 2 times 1/2 times x plus 1/2 squared is 1/4 minus 1/4, nothing's changed here, and then plus 5. Alright, now the first three terms here forms a perfect square. Then we can rewrite it as -2 times x plus 1/2 square, and then minus 1/4 plus 5. And then I'm going to multiply this part out, and we will have -2 times x plus 1/2 square, and then we have -2 times -1/4, that is positive 1/2 plus 5. Okay, so we can look at this function here, because it has negative square coefficient, so it is a parabola open downward, achieves the maximum at -1/2, and then we need to tell the sum of it between the -1 and 1. Okay, because if we plug in -1/2, the corresponding function value is just 1/2 plus 5 equal to 5.5 is always greater than 0. And then we check the endpoint, and that is -2 times -1 plus 1/2 square, that is -1/2 square, plus 1/2 plus 5, and this part is equal to -1/2 plus 1/2, and we have 5. And f1, by the same way, we can find it is equal to -2 times positive 1 plus 1/2 square, and then plus 1/2 plus 5, and this is equal to 1. Okay, so we can see on this whole interval, either at the maximum or at the endpoint, it is always positive. So we conclude that this function is always positive on the closed interval from 1 to 1. From -1 to 1. Okay. Okay. Now, by the test for the concavity, because it is always greater than 0 for the second order derivative, we know that it is a concave up function on this interval from -1 to 1. Okay, so our conclusion is that it is concave up. Alright, this is the second part of this problem. Alright, now we're going to proceed to the third part of this problem. We want to determine on which interval of -1 to 1 is this function increasing and on which part it is decreasing. Okay? To tell whether a function is increasing or decreasing by using derivative, that is, we're going to use the first order derivative if f prime is greater than 0, that means it is increasing. And if f prime is less than 0, that means it is decreasing. Okay? So I'm going to, again, just do the result from part A, because we know that f prime is equal to 2x plus 1 over x squared plus x plus 3. Okay? Alright, now we can see this is a fraction function, and by using the same technique as before as the second part, by using the perfect square technique, we can show that this denominator is always positive. Okay? So you can check this on your own. So it is sufficient to just look at the numerator. That is 2x plus 1. And compare the value of 2x plus 1 on the interval from -1 to 1 with 0. Okay? And by solving a very simple inequality, that is 2x plus 1 greater than 0 and 2x plus 1 less than 0, we can get the solution, that is x greater than -1/2. That means when x is between -1/2 up to 1, because our largest possible value of x is just 1. When x is in this interval, then 2x plus 1 is bigger than 0. And similarly, if we solve this inequality, we have x less than -1/2, and that means x, when x in -1 to -1/2, and 2x plus 1 is less than 0. Okay? So that means this function f, x is increasing on the interval from -1/2 up to 1, and is decreasing on the interval from -1 to -1/2. Okay? And this is the third part. Alright, now let's go to the very last part of this problem. We want to find the tangent line of this function f when x is equal to 0. Okay, so if we want to find the tangent line, we need two things. The first one is the slope, and the second one is the coordinate of the point. Okay? Alright, I will say the second part is easier to start with because we already know x is equal to 0. We just need to find the corresponding function value, that is f0. If we plug in, we know it is log 3. So we have a point that is 0, comma, natural log of 3. So this is our coordinate of the point. Alright, next we're going to tackle the first part, that is the slope. Remember, the derivative can be interpreted as the slope of the tangent line. So basically, the slope is equal to f prime, because we here care about when x equal to 0, that means we're going to have f prime of 0. And we know that f prime x is equal to 2x plus 1 over x squared plus x plus 3. So we plug in x equal to 0. That is 0 plus 1 over 0 plus 0 plus 3. So f prime 0 equal to 1/3. That means the slope is 1/3. Alright. Now if we combine the two pieces together, that is those two pieces, and then we can write the tangent line as y minus f0 equal to the slope times parenthesis x minus 0, because here our x is equal to 0. We care about the point when x equal to 0. And the f0, as what we found earlier, it is natural log of 3, and our slope is 1/3 times x minus 0 is just x. Okay, so our final result will be y equal to 1/3 times x plus natural log of 3. So this will be our final result for the tangent line. Okay, so this is this problem.